In this video, we're going to do three things. We're going to prove that the Poisson probability distribution is a valid discrete probability distribution, and we're going to derive the moment generating function for the Poisson distribution, and also derive the formulas for the mean, which is the expected value, and for the variance of the random variable whose probability distribution is a Poisson distribution. I'm going to do it two different ways actually when it's time to derive the expected value and the variance. I'm going to do it two ways. One is using the moment generating function, and the other one is using the standard formulas for the expectation and the variances. So here we have actually, what I have is a description of a Poisson distribution. So you can read that. What I want to do is actually derive the things that I mentioned. Here are some examples of a random variable that follows a Poisson distribution. Typically, the Poisson distribution is used for probability of, or assessing probabilities of rare events. So if you look at most of these examples, these events are events that are very rare in occurrence. Okay, so let's begin by actually showing that this probability distribution is a valid probability distribution. So I'm going to actually use f of x in the form of a function. Okay, so f of x is given by e to negative lambda to the x over x factorial. This is going to be the form of the probability distribution. And I actually use an indicator function which shows pretty much the domain of the random variable. And remember, the way the indicator function works is that if something that's not inside of that indicator function, the indicator function actually takes on a value of 0. And this is a multiplication, what I have here. So for all x's that are inside the domain, namely all these whole numbers, then the value of the indicator function is 1. Okay, and so here we go. First, to show that it is a valid probability distribution, we need to show that if you sum probabilities, remember, sum of the probabilities must be 1. So that's what I'm going to do. E to negative lambda to the x over x factorial. Now this is one of the easier probability distributions to show this for, because the index of summation is x and it doesn't depend on the lambda, so I can bring e to negative lambda outside of the sigma and then just write the sigma x 0 to infinity of lambda to the x over x factorial. And we recognize the summation, the whole summation, all of the sigma, as a Maclaurin. This is the Maclaurin series, Maclaurin for e to lambda. Remember, Maclaurin series are Taylor series centered at 0. So this will give us e to negative lambda times e to lambda, and that would be e to lambda minus lambda, or e to 0, which is 1. So we just show that this is indeed a valid probability distribution. Now next, let's actually derive the moment generating function. So our moment generating function, hold on. Moment, hold on. Okay, so here the moment generating function is given by the definition of moment generating function is m of t, right? And it's given by expected value of e to tx. And that means I have the sum of, in this case, x goes from 0 to infinity of e to tx times the probability distribution function e to negative lambda, lambda to the x over x factorial. Okay, again, I can bring e to negative lambda outside of the summation and make this go as 0 to infinity, and then combine my e to tx and e to negative lambda. I just factored, so this is going to be simply lambda e to t and then to the power of x. So in other words, I combined these two factors. Okay, and then divided by x factorial. And of course, again, this is the Maclaurin for the expansion of e to lambda e to t. And this we can write it as e2 factor lambda, we get e to t minus 1. Okay, so that's what that is. That is a factorial. Okay, and there you go. So this is the moment generating function for the Poisson distribution. Now, in order to find the mean and the variance using the moment generating function, I need to find the first and second derivatives of the moment generating function. So the first derivative is going to be e to lambda times e to t minus 1, right, which is the moment generating function itself. But that's, I'm taking the derivative of this function. Now remember, the derivative of e to a function of x is itself times chain rule, the derivative of the function of x, the exponent, which is that. The second derivative of the moment generating function is now derivative of the first one. So I'm going to use the product rule here. That's the derivative of lambda e to t times first e to lambda e to t minus 1, right, plus lambda e to t times derivative of the first function, and the derivative of that is going to be again itself e to lambda e to t minus 1 times the derivative of the exponent, which is just lambda e to t. That's the derivative of this part. Now I can actually simplify this by factoring lambda, the GCF. Lambda e to t is a common factor, times e to lambda e to t minus 1. Okay, and that's going to give me 1 plus lambda e to t. I just factored the GCF. Again, the GCF is this, you can see. Once I remove it, I get 1, and then here's lambda e to t. That goes here, the 1 goes here. Okay, and there we have the second derivative. Now that we've done this, actually the expectation is going to be done very easily, right? The expected value of the random variable x, and that's when m prime is going to be evaluated at 0, and m prime is this expression here. Okay, so I'm actually plugging in a 0 for t in here, and when I do, I'm going to get e to lambda times e to 0 minus 1 times lambda e to 0, and this will give me e to lambda 1 minus 1 times lambda times 1. And that makes it e to 0 times lambda times 1, which is simply lambda. Okay, so there's the mean or expected value. Now to find the variance, that would be sigma squared of the random variable x. That's given by expected value of x squared minus expected value of x quantity squared, right? That's the definition of variance. Now expected value of x squared, that would be the second derivative of the moment generating function. Okay, and that is a central moment, of course. So the m double prime, so now I'm actually plugging into this expression. I'm going to put in 0 in this expression. Okay. When I do, I get lambda e to 0 times e to lambda e to t, which is e to 0 minus 1, times I had 1 plus lambda e to t, which is e to 0 minus lambda squared. Okay, so this is going to be lambda times 1 and then times 1 by 1 plus lambda minus lambda squared. E to 0 is 1, 1 minus 1, 0, 0 times lambda, 0. So this expression is e to 0. That's how I got this one. Okay. Now if I tidy up this expression, and lambda times 1 times 1 times the binomial factor gives me lambda plus lambda squared minus lambda squared, and that's simply lambda. So it turns out the mean and the variance are the same for the Poisson distribution. And there you go. So if you have the moment generating function, this is pretty simple. Now what if I want to do it the traditional way, meaning by definition of expectation, and not using moment generating function? So this is the alternate method of finding the expected value. So expected value of x again is going to be x times the probability distribution function over x factorial, and x is from 0 to infinity, right? Now if you actually expand the series when x is 0, the series is 0 because that's 0, x times this part is 0, right? So it starts with 0, and then when x is 1, this is simply e to negative lambda times lambda. When x is 2, this becomes e to negative lambda squared divided by, there is a 2 in x and 2 factorial, that gives you just 1, right? Because 2 factorial is 2, so that's just e to negative lambda squared. Let's just write it like that. Lambda, and then this is lambda squared. The next expression, the next term in this expansion is when x is 3. When x is 3, I have 3x and then 3 factorial. That's going to be just 2 and 1. So that's denominator is 2. So this is going to be e to negative lambda cubed divided by 2 factorial, right? And for the next one, so on and so forth, you can see. So whatever the numerator, denominator is going to be, and the numerator for x, that is. Whatever number you pick for x, denominator is going to be 1 less than that, only in factorial. So I can actually write this now as the sum as x goes from 0 to infinity of e to negative lambda, and then I'm gonna make this like that. I'm gonna go lambda to the x, and I'm just gonna multiply by lambda, and by lambda to negative 1 divided by x minus 1 factorial. I went ahead, in other words, and canceled these x's out, one of the x's. Okay, and now I can actually bring out the lambda outside, this one. Okay, let's bring that lambda outside. So this is going to be lambda, and then the sum is going to go x equal 1 to infinity of e to negative lambda to the x minus 1 over x minus 1 factorial. And now I can actually introduce, let the following variable be x minus 1. First, because x is equal to 1, I'm looking at the index of summation. Subtract 1, so x minus 1 is 0. So if I let k be x minus 1, then I can write this as, remember, this is the expected value of x. The expectation is going to be lambda, And then this is going to go sum k from 0 to infinity of e to negative lambda, lambda to the k over k factorial. And of course, this latter part, this factor, is going to be, that's the PDF for a Poisson. This is Poisson distribution with parameter lambda. Because this is a PDF, therefore, that's going to be 1. That's the PDF of a Poisson. Parameter lambda. So that's going to be lambda times 1 and lambda. So that's if you go through the routine definition of expectation. Now, to find the variance, it's the same approach for the variance. I need to actually find expected value of x squared. Okay. Now, let's do the following. I'm going to write, we know that expected value of x squared is given by expected value of x times x minus 1 plus expected value of x. That's just a rewrite of expected value of x squared. Okay, you can distribute and then take the expectation of each part, and you will see that this would work out to expected value of x squared. Okay, now focus is on expected value of x minus 1 here. So I'm going to write expected value of x times x minus 1. Again, by definition of expectation, this is going to be the sum of x minus 1 times the PDF, right? Which is e to negative lambda, lambda to the x over x factorial, as x goes from 0 to infinity. Okay. Now, again, if you expand this expression, when x is 0, you get 0 here. When x is 1, when x is 1, this factor is going to be 0. Okay, so when x is 0 or 1, the first two terms are going to be 0. And we have the non-zero terms beginning with x equals 2, actually. So, when x is 2, this is going to be 2 times 1. This is going to be 2 factorial, so they cancel. The next term in the expansion is e to negative lambda times lambda squared, right? That's what that becomes. The next term in the expansion is when x is 3. Again, you have the x minus 1 over x factorial is x minus 1 times x minus 2 factorial, and these cross out. So simply have x minus 2 factorial. So when x is 3, this is e to negative lambda, lambda cubed, right? Lambda cubed divided by 3 minus 2, which is 1 factorial. So that's just going to be 1, right? When it's 4, then you get e to negative lambda, lambda to 4 divided by 2 factorial, and so on. So there you go. Just want to show you what that expansion looks like. Now, I can factor a lambda squared from the expression here. Okay, so I'm going to get lambda squared, and I'm going to make the sum begin with 2. Remember, the first two terms are 0, so we can safely begin the index of summation at 2. And then this is going to be e to negative lambda, of course, and then we have lambda to x minus 2 divided by the bottom is x minus 2 factorial. Okay, now this time I can let I'm gonna let k be x minus 2, because look at the index of summation. If you subtract 2, we can actually shift the index of summation back to 0 by making this substitution. So that's going to be k from 0 to infinity e to negative lambda lambda to k divided by k factorial. And again, this is the PDF. What's in here is the PDF for Poisson distribution, parameter lambda. So that's just lambda squared. Okay. Now we can actually find the variance. Now the variance of random variable x is going to be expected value of x squared minus expected value of x, quantity squared. Right? Now expected value of x squared, that's just expected value of x times x minus 1 plus expected value of x minus the last term. Let me use brackets in this one. Bracket and then parentheses squared. Okay, the expected value of x minus 1, we just derived that. That turned out to be lambda squared. Expected value of x, earlier we showed that's lambda, and then minus lambda squared. So you can now combine like terms, and that turns out to be lambda also. So there you go. These are just different ways. There are two different ways of arriving at the mean and variance of the Poisson distribution. Personally, I like the moment generating function. It's cleaner, it's a little easier. So that's my own preference, is doing it that way. But however we do it, we get the same outcome. And with that, we are done with this video. We did what we wanted to do.